Hi, I'm Nick Letherby, the Operating Systems Product Manager for Texas Instruments. I'm going to give you a quick overview and update on TI-RTOS, which is our real-time operating system product, with a particular focus on its support for our MCU and wireless connectivity devices. We're going to begin by talking a bit about the history of TI-RTOS, what it consists of, and the licensing and business model for it. Then we'll talk about specifically the devices and boards it supports, as well as the software development tool chains that work with it. We'll next go into a detailed overview of each component, including the multitasking kernel and connectivity stacks, before concluding with a quick roadmap discussion and also a resources slide which tell you where you can get more information and product downloads. I'll include my email address there, so if you want to contact me directly for more information, please feel free to do so. If you've ever used the TI DSP, you're probably familiar with TI's long history in the real-time operating system market. Back in 1998, TI purchased a company called Spectrum Microsystems, and they had a product called DSP BIOS, and that became extremely widely used throughout TI's DSP base. And in 2010, we upgraded DSP BIOS to sys BIOS and ported it out of the DSP area also onto the ARM architecture and the MSP 430 architecture. Just after TI purchased DSP BIOS, internally we also developed the TCP IP stack, formerly known as the NDK, for our DSP architectures as well. And then a few years ago we purchased Lumery Micro, and that gave us StellarisWare and its USB host and device stacks. TI-RTOS is essentially a fully tested, integrated combination of these proven components: USB, TCP/IP networking, and the multitasking kernel. And then subsequent to its first release back in July 2012, you can see we developed a number of follow-on releases, adding new features and new devices all the time. It's backed up by a team of 12 engineers. And these engineers are very, very experienced. We still have with us the original developers of DSP BIOS. So we have extensive experience with the code base and can ensure a high quality product and a fast response to any bugs you may find. To have a very quick high level look at what TI-RTOS contains, we can see that at its core is a real-time kernel. That real-time kernel sits on a debug and instrumentation layer which helps give you RTOS-aware profiling and debugging. There's an extensive list of device drivers that work out of the box with our different boards, and we have board initialization files which deal with all the board-specific initialization, such as pin muxing, associating the interrupts of a driver. Above the kernel, we have 4 pieces of middleware. We have a TCP/IP stack, which works with our Emacs on devices that have Emacs. Then we also work with the wireless CC 3000 and 3100 families to give you Wi-Fi networking. We have USB host and device stacks with a number of class drivers, a FAT-compatible file system which enables you to exchange data with PCs quite straightforwardly. Then finally we have an IPC module for multi-core communication. This is more applicable to our multi-core DSP and MPU products, but is used in some of our MCU devices such as Concerto, which combines ARM Cortex-M core with a C2000 core. Now, not all TI-RTOS components are available on every single MCU. The main reason for that is that they're not appropriate. For example, wired networking only makes sense on devices that have networking on them, EMAC on them. Similarly, USB, if the device does not have USB, there's not going to be a USB stack available for it. Now, one exception to that is that we are yet to develop the drivers and board initialization code for the C2000 family. So that is a case where we haven't developed the specific software, and it may be available sometime in the future. But make sure you check this chart before when you download TI-RTOS. In fact, in the release notes, we have a similar chart which tells you exactly which components are supported for which architecture, and you can check to see what level of support you get for the device you're choosing. With TI-RTOS 2.0, we changed our delivery mechanism. Previously, we provided a single download that supported all the different devices and device families that TI-RTOS contained. But this was leading to very large downloads. So in 2.0, we now broke that up into separate downloads for each family. So now you look at the device you're using and then go off and select the particular download that supports that device. You've really got two options to access TI-RTOS. With a CCS v6, which is the newest version of Code Composer Studio, the TI integrated development environment, after you install that and bring it up, you'll see it has a link to something called an application center. And if you go into the application center and look at the CCS add-ons available, you'll see that the various TI-RTOS downloads are available through that, and you can install them there. An alternative mechanism, and one you'll need to use if you're using a IDE such as IAR Embedded Workbench, is we have a website where you can go and download these, and that gives, again, full access to all the different downloads and also all versions of downloads. So if you happen to be using a older version of CCS and wanted to get an older version of TI-RTOS to work with that version, you can go there as well. In terms of the commercial side of TI-RTOS, it's really quite straightforward. It's completely free. There's no development or per project license fees. There's no runtime royalties. But we do include both the source code and pre-built libraries. So the pre-built binaries mean you don't have to worry about becoming an expert in building TI-RTOS. You can just run with those straight away. And the source code enables you to have easy debugging. So if you have a problem that you're not sure if it's in TI-RTOS or in your application, you can bring in the TI-RTOS source code and find out exactly where things may be going wrong. Finally, all components except for the USB stack are open source. And when I say open source, I mean a BSD style license, which is extremely friendly. It's not like GPL. There is no requirement for you to ship your source code. So it's a very, very safe license for you to use, but it is completely open source. So there's no proprietary lock-in to TI here. We just want to make development for you as simple as possible. Let's talk a little bit about the different boards that are supported. All these boards listed here have full board support packages in that they have a complete set of drivers, or applicable drivers that is, and also a board initialization file. So you see we support several TivaC boards, Concerto boards, MSP430 boards, and then our most recent addition is the CC3200 Launchpad. In addition to these four BSPs, all the C2000 boards you can easily run the basic TI-RTOS kernel on. We now support a number of different tool chains. Originally, we just had Composer Studio support in our earlier releases. And of course, we continue to support Composer for all the devices. And Composer is probably our most comprehensive solution in that it includes both TI-RTOS-aware Debug plugin, as well as a analyzer tool where you can look at the history of RTOS context switching. And finally, there's a tool called GUI Composer, and I'm going to run through all these different tools in a minute for you just briefly. We've also now support IAR Embedded Workbench, both for MSP 430 and our ARM versions of TI-RTOS. And you can see the various versions you need to use here, but the key point with IAR is we also have TI-RTOS-aware Debug there. We have a plugin for that, so you can again look at whether tasks are ready to run, what tasks are blocked on which semaphore, all that kind of RTOS specific information. And then we also have GCC support. We use the ARM GCC compiler, and we do now give you an option to install ARM GCC with Composer Studio, so you can have a choice to develop with Composer Studio, either with the TI ARM compiler or ARM GCC. And there we have both make files, and we also do have CCS projects if you want to use those. Now let's look a bit about some of these different tools. If we go to the bottom of the screen here, you'll see there's this window here, and this is our RTOS analyzer. And you can see here we have the tasks listed, the task priorities, are they running or are they ready to run? We give you the stack size. So there's a whole series of information you can get about a particular task using this tool. So just imagine you want to optimize the task stack sizes to save RAM. Well, you can look at you can go into a different tab in here. It's actually called the Detail tab, and that would tell you the maximum stack growth. So if you had thoroughly exercised your application, you could check the maximum stack growth and then reduce your stack sizes to just a bit over that to free up RAM for other parts of the application. And this RTOS analyzer tool here is available both in IAR Embedded Workbench and Composer Studio. Now in Composer Studio there's a tool called RTOS Analyzer, and this works a little bit differently to the RTOS-aware Debug. The RTOS-aware Debug is a tool that essentially you stop the processor and then view state. With the system analyzer, you can capture runtime information in a buffer, which you can then either then stop the system, view that buffer, but also you can stream those buffers off the embedded target up to the PC using, say, a UART link, for example, and then capture a large amount of data up on the PC and then view a lot of execution history. And what this analyzer does is, as you can see here, we've got 3 different tasks, and what it's showing you here is the context switching. This is a very simple application which mostly spends most of its time in the idle loop, which is the blue line here, but occasionally we're context switching to this task function and then to the task 0 function up on this line. So you can see what this shows you is task execution history. Additionally, you can look at CPU load per task if you want to see is one of your tasks particularly taking up a lot of CPU cycles. And you can also look at individual log data where you can print out specific statements, debug statements relevant to your application, and you can have that all correlated because this is all time stamped here, so there's an actual real timeline below here so you can cross correlate different events. Finally, a new tool that's come out in Composer Studio is GUI Composer, and what GUI Composer allows you to do is to mock up user interface of your embedded application. So you can both control it from, for example, a knob, just like you might on the real instrument, and you can also then view the output as you might on the real instrument. So this is a great what I call system level debugging tool, because now you can really interact with the embedded system as the customer would. You can see, are you getting the type of output you expect? So with the way GUI Composer works is that it allows you to mock up this screen, and this interface screen works in HTML5 that runs on a web server, and then that web server communicates through the CCS debug server down to the embedded target, where it can both read data to bring data up for display in the UI, or you can write data. So if you've turned a dial and need to change the way the target is behaving, the input from that dial will then be fed down to the target into a variable and changed. And there's really two ways you typically communicate to the target. One is via JTAG, but of course it's not always possible to get JTAG connections into your system, especially once you get away from a benchtop environment. And one thing that TI-RTOS offers is it offers a simple UART little monitor program that communicates back to the TI-RTOS UART driver up to this debug server. So you can have a non-JTAG way to communicate between this user interface and the embedded target. Now we've looked at the overview of TI-RTOS and the development tools you can use with it. I want to jump into some of the individual components in more detail. We're going to start off with the real-time kernel and its associated power management and drivers. The TI-RTOS kernel is designed from the ground up to be real-time, and what that means is that our system calls are deterministic and they execute in a predictable time. And as you can see from the bullet points at the bottom of the page, we provide detailed benchmarks so you can see exactly how long, for example, a semaphore post takes. How long does a semaphore post take when there's a context switch associated with it? So you can look at the different parts of your application and see, if I want to complete this response to an interrupt in this particular time, can I make a semaphore post, have a context switch, run this function of the task, and be sure it will execute in that time? We give you the type of information that enables you to make those informed decisions. In addition, we work very hard to keep interrupt latency to be as low as possible and disable interrupts for only short periods. And then finally, we also have a feature called zero-latency interrupts. So on our Cortex-M RTOS implementations, you can specify one or more high-priority interrupts to be completely free of any disabling by the RTOS if you have very, very hard real-time interrupts you need to respond to. Now, those zero-latency interrupts cannot interact directly with the OS, but that's typically not a problem, and it's more important for you to maybe be able to service an hard real-time event without actually having to experience any OS latency at all. On the C2000 architecture, we have something called reduced latency interrupts, where because of the architecture we can't make them completely zero latency, but we still have OS interrupt latency reduced to just about 14 or 15 CPU cycles. In addition to real-time performance, another key issue for MCU developers is memory footprint. TI-RTOS is inherently a low footprint, and the kernel is highly configurable. So, for example, if you're not using events in your application, it just won't, that code won't be linked in. In addition, we provide something called static configuration. So while you can certainly have programmatically create things like tasks and semaphores with task create calls and semaphore create calls, you can in fact statically create these at build time and eliminate the need for dynamic heaps or that create or delete call code in your application. That can save you, a couple of K of code. In addition to timing benchmarks, we have the same benchmarks include sizing information. We have an application note on how to minimize kernel footprint, and we have a minimal kernel configuration example where we've pulled out all the, say, real-time analysis buffers and various other debug type features that can pop into the kernel and increase a RAM footprint. So we have a minimal kernel configuration, which is a great starting point. The kernel services really consist of two forms. One is a set of device-specific services, and these services will vary a little bit by device. So we have interrupt management, which of course is really available on every single device, and we also have timers, which again are available on every single device. Now then we have some other hard device-specific services such as power management, which will be available on some devices that support power management, but not on others. And then we also have exception handling, which is specific more to Cortex-M, which has exceptions and not present on some of the other MCU devices that don't have exceptions built into their architecture. Around these device-specific services, we have a set of generic RTOS services available on every device. At the bottom of the screen, you'll see we have multi-threading. So we have tasks, which are your traditional tasks, and these are independent threads of execution. Each has their own task stack, and they can yield the processor, so they can pend on a semaphore. And the way a task typically works is you have an infinite loop that loops around, infinite processing loop. It keeps looping around, and then it will yield at some point by pending on a semaphore and waiting for, say, some I/O from another task or from a I/O device. A second type of thread we have is a software interrupt. Now, a software interrupt is different to a task. It can be preempted, but software interrupts cannot yield the processor, and they also cannot. They also all share a common system stack. So if you are in a very, very low memory footprint situation, you still want to have some level of preemptive multi-threading. A software interrupt allows you can have several software interrupts. They all share a common system stack, which means they are consume less RAM than multiple task stacks would. And the threading model is somewhat simpler because it's purely preemptive. So a software interrupt will execute until it finishes unless a higher priority software interrupt or an ISR comes in and changes it. And then finally we have clock threads, which are essentially periodic functions. So if you have a function you want to run every 3 milliseconds, for example, you would use a clock thread. And at the bottom we have the idle loop, which simply is where you drop into when there's nothing else doing your system. Now, in addition to the different multi-threading, we have various inter-task communication. So obviously you have things like semaphores, where we have both binary and counting semaphores. We have gates, which allow you to provide critical control access to critical sections, data sections. We have mailboxes, which provide fixed data exchange between different tasks. And we have events, and events essentially allow you to have a task wait on multiple events. Let's say you have a task, for example, which you want to block on while it's waiting either for a mailbox to post to it, or maybe it's also waiting for some I/O from a particular peripheral. So what happens, you can then have an event and have that event be woken up either by the mailbox post or by the semaphore post from that I/O event, and then the task will wake up and start processing. So it allows you the task to basically go to sleep and waiting on different events to wake it up, rather than sit there polling, checking, is this semaphore being available, is that semaphore available? Then we have memory management. We have variable size heap and fixed size buffers. And our variable size heap has a multiple implementations, including a hybrid heap based on multiple fixed size buffer pools, and that gives you both variable sized allocation in a deterministic manner. We also have a more malloc-like heap, which is not as deterministic or high performance as the hybrid implementation. And then finally, we have a set of debug and analysis features. We have a logging built into the kernel, so you can log out events. We have diagnostics, which enable you to turn logs on and off, which is very important. So if you want to include logging into your final application to give you remote debug capabilities, if you have something go wrong on a customer site, you can basically have these diagnostic masks. You can turn everything off, and then you can then access those and start turning them on to look at logging functions, get some idea of what went wrong. We have stack checking, so you can check how big is a stack, was there stack overflow, and that's a very useful feature because if stack overflow appears, you can, if stack overflow happens, you often don't know about it until you start executing garbage, many thousands of CPU cycles further on. Because we have stack checking, you can simply, every time there's a context switch, for example, you can call one of these hook functions, which is another feature we have. We have these hook functions. That enables you to insert custom functions when a task is created or deleted, and when a task context switch occurs. For example, you could have a hook function called every time there's a context switch, and you can go and check the size of that stack and whether there was overflow. And if there was overflow, at that point you can halt the processor and start understanding why there was task overflows. You can catch the problem before it manifests itself in a system crash. So the kernel itself obviously contains, has all the basic multitasking functionality you're used to. Now, one area where TI-RTOS is superior to most other operating systems out there, or at least real-time operating systems, is in power management. Before we go into some of the features we have, I want to talk about why it's important for an RTOS to have power management, and why an RTOS is actually a benefit to power management in an embedded application. So let's think of some of the generic features of an RTOS and how they help low power. Well, one is that in an RTOS-based application, you're interrupt driven. So you wait on interrupt from, say, a peripheral and then go and process it. So you're not polling anymore. A lot of microcontroller applications like to poll to see if an interrupt occurred, and obviously polling is very wasteful of power because you're having the CPU loop around just continuously checking a particular register for I/O. You don't want to do that if you want to save power. And the other nice thing about the RTOS, you remember we had the idle process that you drop into when there's nothing to do. Well, obviously that idle process, when you're in there, you inherently know there's no system functions you need to do, so you can then go off and do some go into some low power saving mode in the idle process. So you can see right away that using an RTOS is like to save you power because of the way the application is now structured. In addition, the RTOS is a good place to control power management for some other reasons. One factor to consider is that typically an RTOS has a system tick, that you typically have a system tip going, and that's used to control your periodic functions or timeouts. And obviously if you're doing power management, you start wanting to say turn off a particular clock. You don't want to turn off a clock that's driving the RTOS timer tick without the RTOS knowing about it. So again, it makes sense for the RTOS to be controlling power management, so it's turning off timers, and it knows about that, so it can keep its time base accurate. Secondly, when you get into more sophisticated power management capabilities on silicon, imagine, for example, you've got clock gating and power domains. So let's take a scenario where you have a SPI peripheral and you have a UART peripheral, and they're controlled by a serial power domain. Well, to turn off that power domain, you need to be sure that neither the SPI is being used or the UART is being used. And one of the nice things here is that if you make your drivers power aware and build some power management intelligence into the RTOS can basically be told by the driver, oh, I'm using the SPI right now. And so it's aware when the SPI is being used, and then when the driver finishes, it tells the RTOS, I'm not using the SPI anymore. So the RTOS will know inherently when the SPI peripheral is in use and when that UART peripheral is in use, and it will then, once they're not in use, it can then say, oh, I can go and power down the serial power domain. So having a common place to track which peripherals are active, which power domains can be powered down is very, very useful. And then finally, of course, as we pointed out earlier, is the OS knows when nothing is happening because you're in the idle function. And then secondly, it also is aware of potential future action. So while obviously the OS cannot predict when exactly every peripheral interrupt occurs, it will know if a periodic function is scheduled in 3 milliseconds time. It also will know if there's some type of a timeout scheduled in several milliseconds time, and that way it can be aware that maybe for the next 2 milliseconds the processor is really going to do absolutely nothing unless some external interrupt occurs, and that enables it to make some decisions about going into more aggressive low power modes. So if we look at the situation of TI-RTOS Power Management today, we have a feature called tick suppression, which I'm going to explain in more detail in a minute, and CPU idling in the MSP430 today. But we don't have some of the more powerful power management framework features I started alluding to in the previous slide, because the hardware features are not there. There's only fairly limited clock gating on the MSP430. Now on the CC3200 and some other future MCU devices I can't yet discuss with you, we will have not only tick suppression but very, very powerful power management, where we have clock gating, multiple sleep modes including very deep sleep modes like hibernate. We'll have something called a power policy, and these are all under development now or planned. You'll start seeing production releases in Q4 2014 with this full power management framework on various MCUs and wireless connectivity devices. To talk a bit more about what tick suppression is, let's consider the situation. As we said, an OS, every operating system will typically have a system tick that goes off, we'll say, every millisecond. Now, when you get into a power saving mode, what you don't want to do is be waking up the processor purely to service this OS timer tick. That's pretty wasteful, because then you're pushing the CPU out of a low power mode just to handle this timer tick and then see that, oh, there's nothing to do, and then you go back to sleep. So what happens with tick suppression is the TI-RTOS will work out when you really need to wake up. So if you look at these diagrams here, you'll see in this diagram here we've got a 1 millisecond timer tick that's independent of the OS, and that's just to show what a 1 millisecond interval looks like. And without tick suppression, you see that here we've got an OS tick that's every millisecond. You see that the OS is popping up. There's an interrupt timer tick coming in every 1 millisecond. We'd be waking up the CPU, processing that, seeing there's nothing to do, and going back to sleep. Now with tick suppression, you see we get a lot smarter. And what happens here is the OS now knows that I don't need to have this OS tick go off unless it's associated with a specific timeout or periodic function. So it suppresses a lot of these timer interrupts except when they're absolutely needed. So you can see here that we're eliminating probably about a good 80% of timer interrupts, and that means that when you're in that low power sleep state, you don't need to now worry about all these ticks. You're getting far fewer of them, so you're going to get much, much better power saving. So this shows you here that tick suppression is really a very useful feature in low power mode. And the TI-RTOS implementation is really straightforward. It's purely a configurable option that you just set the tick mode to dynamic, and there's no need to be programming APIs to turn off ticks and then turn them back on. It's all done automatically for you, so very, very easy to use compared to some other OS implementations. Now, if we talk about our more full-featured power management framework, the purpose of the power management framework is allowing you, the customer, to easily access the power-saving hardware features. So in reality, these can be quite complicated to use. In one sense, there's a whole series of registers you have to program to go in and out of these different sleep modes. There's all kinds of coordination you have to do to make sure that is this driver or is this particular peripheral not active before I can turn off this power domain. And then finally, another problem is that going in and out of deep sleep modes often tends to expose silicon errata, and then you then have to be aware of all these silicon errata and the various workarounds for them, read all these very detailed app notes, and that becomes very time consuming. So the purpose of our power management framework is really to insulate you, the customer, from the specifics of all the power management. So you're not worried about, how do I manage this transition from Hibernate and out of Hibernate and have to worry about this specific sequence of instructions and power down. You don't have to worry about any of that because the power management framework deals with that. It provides you a set of fairly high-level APIs you can use, and it deals with all the coordination of making sure that we know that this driver is not being active right now, so we can power down this power domain. It can just determine, for example, let's use this more deep sleep or better power saving state because I know that all these different domains are not active. And then finally, it's optimized to really minimize footprint in the MCU space. We've actually had this power management technology for probably about 6 or 8 years, and we used it with our mobile phone devices with Linux and Android, and obviously Linux and Android and mobile phones have a lot more memory than MCU. So when we took this into the MCU space, we did some pretty extensive optimization to make sure the footprint was low as possible. So if we want to talk about some of the more of the features here, where we're going, one is that all our drivers in TI-RTOS are going to be power aware when they're being used on a device that has this power management feature. And what drivers do is a driver declares a dependency, as you'll see from some of the APIs in the next slide, on a clock and a power domain. So the driver goes and when the driver starts, it goes up and tells the OS or the power management framework in TI-RTOS that I need the, say, serial domain and I need the UART clock. And so therefore the OS is now aware those are being used, and when the driver then stops executing, it basically releases those dependencies. And so that enables the OS to, when there's an opportunity, when you've dropped into the idle function, it can quickly look around and say which domains are here are not active or don't need to be active. And also when the OS moves to a low power state, it also allows the drivers to register with it, so it can notify the drivers if it's going to a particular low power state. So if the driver, for example, has some associated DMA activity going on, it can tell the power manager, just give me a little bit of time here to complete this DMA to make sure that any suspend or resume operations happen gracefully and everything is shut down in an orderly manner. Secondly, communication stacks also need to be power aware. So imagine, for example, you've got a Wi-Fi radio on, and if that Wi-Fi radio is active and the Wi-Fi stack is communicating with the radio, you don't want to shut down the radio until the stack tells you it's finished the transmission. So again, what these stacks go is these stacks can declare constraints to say don't power down while I'm using the radio, and that way the radio is protected from any power down operations until the stack says it's safe to power it down. And then we then provide a power policy which is automatically run in the idle process to achieve the most aggressive power station, so saving. So you, the user, don't have to worry about, do I have to turn off this or turn off that. We'll just power the device down in the most power saving mode possible, just automatically. Now if you want to customize this, you can, you're welcome to, but the point I want to stress here is that we do provide a lot of very aggressive power management available out of the box, with will do, with no need for you to use it. Then to talk a bit about the APIs, we have, as I said, I talked about, we have this set and release dependency and set and release constraints. That enables the application or the drivers to go and set these dependencies on things like power domains and clocks and everything. Then we have a power sleep mode. So again, there's multiple power sleep states. We might have a standby state, which you just drop the processor into a standby mode and all the MCU logic is maintained. Then we have a power down mode where, for example, we actually completely shut down the MCU and we store its register context in some non-volatile memory, and then on power up, we can then, when we do the save, we do the restore on power up, and we bring them back in. So that enables a lower amount of power to be consumed. And finally, we have a full shutdown when you're simply shutting the whole device down and just rebooting. And then also we have these register and unregister features. So again, you may want to have a device registering to be notified that a shutdown is going to happen, and that way the device can say, oh, I've got to go and I need time to finish this DMA operation. And in that sense, this enables the OS to be aware of all the different things happening. It can then make sure that when a shutdown occurs, it's been graceful, all the application is wrapped up, anything's outstanding, it's safe to go down. You go into that power saving mode, and then you can then come out of it knowing what you have to restore. So again, this is a very sophisticated power manager, but it's also very easy to use because you, the user, can really just let us do TI-RTOS do most of the work. So that covers the power manager. I want to talk a little bit about our drivers and board support components. So there's a few things to know. Firstly, a lot of you are probably familiar with things like TivaWare, Stellaris-ware, or MSP430-ware. And these are basically low-level peripheral APIs. They're very specific to a device. And this is a very important library that we make a lot of use of in both our drivers and especially our initialization file. So our drivers here, these drivers here, are board independent. And what these drivers do is they provide you a standard cross-platform API. So we have UART read, and UART read is on every single UART device we support. So the UART read is there on MSP430, on TivaC, it's there on CC3200. So it means that whenever you pull an application from one MCU to another MCU or another WCS device, you are going to get that UART read, and it's completely, makes your code extremely portable. Now, these drivers, I said, are board independent. And the reason they're board independent is all the board specific initialization is done in this board.c file. And that's where things like pinmuxes and everything else are set up that are board dependent. So I'm just going to go through each of these components in a bit more detail if you're not familiar with them, so you can understand what they really do. So let's look at TivaWare. And this is your TivaWare or MSP430-ware. These are the low-level APIs, and you can see there's typically dozens and dozens of these low-level APIs, and they'll often be setting individual flags inside of a register. And what this does is they just abstract away the details of the particular register, so you have a nice symbolic interface to manipulate that register rather than working out that bits 4 and 5 of this register have to be set to set the parity, for example. And what happens is that these APIs are used by both the board.c file for initialization and also by the UART driver itself to control the UART's functionality. So you do not typically see these APIs at the TI-RTOS level. Then we have the TI-RTOS driver APIs, and so these are a very, very standard documented API set. Here I've got the UART APIs, and you can see there's 6 UART APIs. UART init, which is initializing the driver's data structures to the OS. It's not doing any hardware initialization. I'll explain that later. We have the UART params init here, and the UART params init is where you would set things like number of stop bits, for example, that the UART needs, number of parity bits, that type of thing goes in, set there. Then we have a UART open and UART close, which you do when you want to open up a UART port or close it. And then finally, you're going to read and write to that UART port. So you would read from it and write from it. So these are really the 6 APIs you would use all the time. There are a few other APIs, things like specialized non-blocking reads and everything that you could rarely use, but they typically would not be commonly used. Now, if you look at the UART driver implementation, this is a very simplified pseudocode implementation just to show you what the UART read function looks like for a TivaWare device, TivaC device. So you can see, it's actually UART write, in fact. So we have UART write happening here, and then the first thing we do when we go into this UART function is we're going to append on the semaphore, and what that would do is that that basically means that we're blocking out access to that UART for other threads. So that means you've got thread safe access because we're appending and posting to this mutex to make sure that only this particular thread can access this UART at that time. So you don't want another thread to be able to come in and overwrite the UART registers and cause all kinds of corruption. Then you'd make your TivaWare call, for example, writing out the character to the UART. And then the second thing is that you would then append on a different semaphore, waiting for that write to complete. So the point here is that this is a blocking driver. We're not polling in the drivers. Generally speaking, we do not poll in TI-RTOS drivers. There are maybe a very few rare occasions when we do, and but typically our drivers are all blocking. And so we would then wait for that ISR to complete, and then while we're waiting, another task can be running and using the processor for some other functionality. Then finally, we got the board.c file, which is where the peripheral initialization. You see here, this is our init UART function in the TM4129 launchpad, the connected launchpad. And in here, you can see this is where we're enabling the peripheral, the UART peripheral, where starting to configure things like the pin max, the pin mux. Also, this is where you would connect up the particular, you'd say this is where you want to say, do I have 4 UARTs or 5 UARTs? Which UART is associated with which interrupt vector? All that type of thing is done in this file. And the nice thing here is that we isolate all the board specifics into one single file. So when you're porting from, say, the TI launchpad or development kit to your custom board, you simply come to this file and make the modifications you needed for your custom board, and then the rest of your application does not change. So the rest of your application comes over, very, very cleanly without any modification. You just change all the specifics in this board.c file. Let's move on to talk about the various middleware components that TI-RTOS includes. We'll start by talking about the USB stacks and the FAT file system. USB features both a host and a device stack and a number of class drivers. We have MSC, mass storage class of this host, and we have HID, which is human interface device, things like mouse, keyboard, and various other pointing devices, and then CDC, which is communications. We have a device class driver there. And we have examples for each of these class drivers. And as you'll see when we talk about the FAT file system, the next slide, we actually have a complete end-to-end example of showing you how you can write to a USB flash drive using the FAT file system, all in pre-configured and built up for you. In the file system, we use a FAT file system that's open source called FATFS. Again, the license on that is very, very BSD-like, so again, no contamination of your application. A few important features to note. Start off with the drivers. We actually I talked about earlier, we have a USB flash drive example where we have a complete working example where you write out to PC compatible files onto a USB flash drive. We have something for an SD card. We have a SD card drive that works via the SPI interface, and you can write out PC compatible file systems onto an SD card. And so both these are fully implemented working drivers you can use out of the box. Then as well as the native APIs to FATFS, if you prefer to use C runtime library APIs like fopen, fread, fclose, those are all available. We can basically plug the RTS APIs on top of the FAT file system. We support all the FAT12, FAT16, and FAT32 examples. Now, long file names are supported, but not in the default build. And the reason we do that is that there are still one or two outstanding Microsoft patents associated with long file names and VFAT. And we do not, TI does not indemnify against use of those. So you should investigate whether or not they would affect you. Some of those patents have expired recently, but there are still one or two patents that might be applicable still around. So again, we have FAT compatible file system, and that contains all the operations such as formatting, media, all the things you're used to there. Let's move on to the networking side. On the networking side, we have a complete IPv4 and IPv6 compatible stack. Obviously, it has a standards BSD sockets interface. It also has a zero copy sockets interface available, so if you don't mind moving away from BSD sockets and want to save CPU cycles and memory by eliminating copies, you can do so. The stack itself is configurable, so you can pull out modules you don't need to reduce the code size, and also the buffers, all the buffers are also configurable, so you can manipulate the buffers to free up more RAM by having smaller or larger buffers. And we have a number of new features due for release in Q4 of this year in our 2.10. We'll be integrating the HTTP server with the FAT file system. Currently, the HTTP server has its own built-in file system which works with a memory-based file system. We'll now make that work with the FAT file system, so you can plug in an SD card and read files off that. And we actually have an application though on how to do that today, but it will be formally built into the product later this year. Then we're also going to be making our network applications. Those are the boxes you see up on the top of the screen here, things like SNTP, HTTP, DNS. We're going to be making those work both with they already obviously work on this TCP IP stack, but also we want to make them work with the built-in TCP IP stack that comes with the CC3100 wireless device. And so we're in the process of making our HTTP server work over both those stacks. And that will again mean that you'll have a situation where you can swap from a MCU with a wired Ethernet connection to an MCU where you drop in a Wi-Fi connection instead, and all your network-based software will come over transparently. And finally, we're also in the process of releasing SSL and TLS. This network security software, and that actually will be before Q4. It'll be coming out in Q3 of this year. And I'm going to talk a bit about that a little bit more in a minute. So firstly, what is SSL and what is TLS? Really, a lot of people are familiar with SSL, secure socket layers, and that essentially that standard got renamed to transport layer security. That's TLS, and then another new standard that was created was DTLS, which is datagram TLS, which of course works with UDP. And you can see what's happened starting about the turn of the century. TLS versions started coming out, and at this point most browsers, obviously browsers work with SSL 3.0, they work with TLS 1.0, and a lot of them work with TLS 1.0. Some of these newer standards like TLS 1.2 and DTLS 1.2 are not yet widely adopted by browsers, but obviously will come to the fore in the near future. So essentially what we're talking about here is network security software to enable secure connection between you and the embedded target. We did not write this code ourselves. We licensed it from a company called wolfSSL, who has a product called CyaSSL. So unfortunately, this won't be a free product for our customers. You'll have to pay just under $3,000 for a commercial license, and that will allow you to deploy an unlimited number of copies in a single one of your products. And we have a GPL licensed version, so you can use that for evals, and then when you want to come to actually ship it, move more into production environment, obviously you replace the GPL licensed version with the commercial licensed version for money to avoid contamination in your product. Then there'll be a part number for this, and you'll be able to purchase it through the TIE store. In terms of the support model, we will provide the front-end support, and we obviously can work specific issues with wolfSSL themselves. And also wolfSSL has a forum that you'll be able to post questions on as well. So there'll be two ways for you to get support. And if you get, for very in-depth support, you'll either need to contact TI and we can talk to wolfSSL for you. But you also have an option, if you get a very in-depth support question, to separately get a support contract with Wolf if you want to get direct face-to-face time with them. CyaSSL is a pretty complete product. It's firstly, the most important thing is that it's optimized for embedded. OpenSSL is a very, very large piece of code, not suitable for embedded applications. And with the SSL and TLS we have on TI-RTOS, that will scale down to as small as 20 kbytes as a minimum code footprint. It does, as I point out, support all the latest standards and, importantly, a broad range of ciphers. So includes a pretty extensive cipher library of hash functions, block functions, all those public key type things you need. So you've got a good range of ciphers, and they're being added to all the time by Wolf, and we'll be continuously upgrading the product as they make new releases. And with network security becoming a major issue these days, we really anticipate that SSL TLS will be something that pretty much every networking customer is going to want. Let's talk a bit about the roadmap. This slide tends to summarize the recent releases we've had over about the last 6 months. And our next, we'll probably have maybe some minor releases between now and Q4. Our next major release is 2.10 coming out in the 4th quarter. Now there will be 2 new devices supported in that release, and I can't tell you. You'd have to get an NDA and talk to your TI sales contact. But we're going to be making a number of improvements, especially in the IoT communication space. So As I said earlier, we'll be having things like HTTP server run over both Wi-Fi and wired. We're also going to be adding MQTT support, and also HTTP client as well, which is a key component of a technology called REST, which is becoming very popular in the IoT space. We'll be adding additional drivers such as a real-time clock driver. And then finally, this is where you'll see the power management framework I discussed earlier will start appearing in Q4 with some of the devices there. So for more information, we have a TI-RTOS webpage you can go to, and that has some information plus a product brochure. We have an E2E forum where you can go to ask questions or to search for topics. We have a wiki where there's a number of detailed app notes which can be quite useful on configuring some of the subcomponents. And then we have the download page I discussed below. And then finally, if you want to contact me directly, feel free to use the email address up there, quite a straightforward one. I'd like to thank you all for taking the time to view this presentation. But before you go, let me just quickly summarize TI-RTOS and some of its benefits. Really, the reason we did TI-RTOS is to enable you, the embedded software developer, to focus on your specific area of application expertise. There's a lot of new technologies coming into embedded apps, such as connectivity is becoming very, very important. With IoT, space, not only is connectivity important, but obviously power management is now becoming important, because you may want to have some type of IoT sensor that can run for a year or more on a very simple battery. So with TI-RTOS, we're ensuring that technology and those capabilities come to you out of the box, and they're all pre-integrated and tested together. So you have a solid software platform you can start development on and just get on and add your application added value. In addition, TI-RTOS provides a standard platform across all different TI devices and abstracts away differences between, say, UARTs, between, say, an MSP430 and a TivaC device. And what this means to you is that once you've invested in an application on a TI microcontroller, you can very easily move to another TI microcontroller using TI-RTOS. You don't have to change large amounts of code because you haven't got that code all intimately bound up with the specifics of the UART register for an MSP430. We do work with multiple tool chains, so again, we're not asking you that you have to, say, develop with Composer Studio. If you want to develop with IAR Embedded Workbench or GCC, you can use those tool chains. And then finally, there's no real commercial barrier to deployment. We tend to find that a lot of embedded developers in the microcontroller space would like to use an RTOS, but they're often deterred from using it because they don't want to make the commitment to invest $10,000 or $20,000 to bring it in. With TI-RTOS, there's no cost licensing. There's no commercial reason not to just come and use it because it doesn't cost you a dime. So again, thank you for attending this, and I hope you get to use TI-RTOS in the near future. Bye.